Let's start. Today I'm going to start by talking about bicycles. I'm also going to talk about bicycles next class in a different way than today. But our main topic today is going to be particle motion relative to a frame, which is this relative motion business, which is hard for you, I think. And I'm going to start with a path coordinate problem. Before that, I wanted to show you this picture. Who has seen a picture which looks like this before? Raise your hand if you've seen a picture like this. Wait a second. Too many people raised their hands. I don't believe it. Like this means has all of the interesting features that this picture has in it. Now, when I say all the interesting pictures, features, you can't maybe get all of them. For example, this is my next door neighbor Jonah's right calf. That's interesting to me, but maybe not interesting to you. Not that interesting to me, frankly. But my next door neighbor's mother, he's a kid, sent me this picture, and I said, fantastic. So now, what do I mean seeing a picture like this before? Look at the spokes of the wheel. You know what the spokes are? Anybody not know what the spokes are? Who knows what the spokes are? Okay, ask your neighbor if you don't. Anybody? Who has seen a picture of a bicycle where the spokes look like this before? Raise your hands high. And have you thought through why they are like that? If you have thought it through before, you're not allowed to answer. Okay, now the question is, why do the spokes look like this in this picture? I would like to hear some theories. Yes?
The parts of the spokes towards the outside are moving faster, so the shutter speed of the camera causes weirdness.
Parts on outside moving faster. And then what did you say about the camera?
There's a certain amount of exposure time. So the
Exposure time causes weirdness. Okay, that might be a partial explanation. Anyway, any other explanations? Or more detailed explanations? Yes? That's an observation, yes. Now, that is true. The ones at the bottom are much more spaced out. Yes?
And that might be because the spokes near the ground are moving relative to the ground.
Spokes near ground are not moving relative to ground. And why would that? Why would that cause them to be spread out?
Well, I was thinking the spokes are spread out to begin with, but the spokes on the top, they're actually repeats to the same spoke.
Repeats of the same spokes. Top spokes are repeats. Somebody who thinks they've got it but they're shy? Okay, yes?
It might have to do with the camera following the bike, and so the spokes on the bottom are going much faster with respect to the camera, whereas the spokes on the top are like much slower with respect to the camera, and so something with the better causes more spokes on top to get recorded.
Camera following bike, so spokes on top are going faster. Spokes on what? Oh, spokes on bottom going faster. Any other theories? Come on, the bike experts, the people who've seen this picture before. Does anybody here know how a picture like this is taken? Does anybody even understand what this picture is, what kind of camera it is, or anything like that? Anybody here know about horse? You do. What is it? Go ahead. Do you know it from biking or from horse racing or
From racing.
bicycle racing?
No, from foot racing.
Foot racing, yes.
I think it's like a scanning slit camera.
A standing slit camera. A scanning slit camera, which is what?
It just looks at the finish line.
It just looks at the finish line. It just, say again?
It records those pixels.
It just records the pixels on the finish line. It's a vertical line. Scanning. Okay, so this is what this picture is. It's called a scanning film finish line camera, something like this, and traditionally they're used in horse races. So this is an unusual camera. I assume that this is a digital simulation of an unusual camera, but I think it goes back to about 1900. I have never seen this of a bicycle race before, actually, and I looked on the internet, and there are practically none of these images on the internet. So this must be a brand new bicycle race technology, or it's not brand new? I found very few images on Google like this, but I guess in a year we're going to see them all over the place. But in horse races, they're used all the time. So here's what this camera is. The camera, instead of having an image plane, it just has an image line. And the way these pictures were originally taken is, for example, you could imagine that you have a camera with a lens in the front, and in the back there's a whole picture of horses or the horse track, but you put a black shield in the front of it, so only one line is exposed, one little slot. Then, as the horse race goes on, you take the film and drag it behind that line. So what's exposed on the film is a scan of the finish line. And this is why these streaks are going right across here like this, because this is actually the same picture taken again and again and again and again and again. But then a bicycle gets in the way, and you don't see the background. And now it's a picture, and the picture is a picture of this scene, but now we're looking at the film, so it's smeared out again. Then they take that film and they scan it by just at the right speed so that the bicycle wheels are about round. If they scan the film by too fast, the bicycles would be fat oblongs, and they scan it too slow, the bicycle wheels would be narrow ellipses. And actually, you can see they don't get the speed quite right, and they really can't get the speed quite right because different bicycle riders are going at different speeds. So the slow rider, relatively slow, has a tall wheel because not much goes by of the bicycle as the fast riders get tall wheels because they zip by the film and only occupy a small part of the film, and the slow riders get big fat wheels, relatively fat. So here's Jonah, my next door neighbor, first place in this race. Now why does that scanning give these funny shaped spokes? Yes? Because the spokes what? There are different positions, but there are different positions in different ways. And now we have to go back to the sort of the explanation that we were getting before. Imagine, where is the finish line in this race? The finish line is right here, let's say. And what happens is this piece of the wheel doesn't move at all. So this piece of wheel gets exposed for a long time, but time on this picture shows up as space because the film is scanning behind. So this spoke is blocking the finish line for a long time, so it's fat. And it's not moving. So a long time goes by before you see any of the other spokes, because the film is scanning by and this thing isn't moving. Whereas at the top, those spokes are moving twice as fast as the bike is moving, and as the film goes by, spoke goes by, spoke goes by, spoke goes by very quickly, so they're all bunched up together at the top. Now let's see. My plan was to go like this, A, B, C, but I couldn't help myself but give you the explanation, so I don't know how to make a quiz out of this. I'll have to make a quiz later on about something else. It's like telling the punchline of the joke before the, anyway, I screwed it up, quiz-wise. Okay, so now I have a challenge for you. This is a project. If people want to do projects, draw the shape of the spokes in a bicycle using calculations. And get MATLAB to draw you the shapes of those spokes. And as many people as want can do this, but you have to work separately. Okay, that's my challenge for you. Any questions about it? Any questions about my explanation? What's the purpose of this camera, right? This is what they call, in horse races, there's a phrase called photo finish. This is what it's about. They use these images to figure out who wins the race, because they have a picture of the finish line at a whole sequence of times by the film streaking by. And you see, if you look in pictures of horse races, sometimes in the background you'll see on the wall pictures, these scanning images of horse races. Any questions about this at all? Who kind of understood what I was saying? No. It's an interesting thing. I mean, it's a twist in your brain to think about time and space and so on with this film scanning behind the slot. Okay. Who said scanning slot camera? Who's ever heard of this before that one guy? And in what context? Foot races? What? Rowing races. They use these also for the finish line? But in none of those races do you get this beautiful thing here. So my friend Jim Papadopoulos, who's my bicycle expert friend, he's a co-author of the book called Bicycling Science. I showed this to him this weekend, and he hadn't seen it before either. And he said, that's beautiful, so I thought I should show it to you. Okay, ready to go? Next topic. All on. We don't know what the quiz is yet. All on wasn't so successful. Okay, I'm going to start out with a kind of a path coordinate problem. It's a simple problem, but it's one that I think perhaps none of you could have done before this course, and you should be able to do now. So the problem is we have a bead on a stationary wire, and the question is, how does it move? And at a glance you would think, oh, this just looks like the same kinds of problems I should have been able to do in high school. But as you have noticed by now, in almost all of your courses in high school and college, we snake our way through exactly those problems which are easy to solve and don't show you problems that look equally difficult that are hard to solve. So this is one of these problems that looks equally difficult but is relatively hard to solve, as in most freshmen would not be able to do it. But it looks easy. Here's how it goes. Let's say we have a wire, and this wire is rigid, and the shape of this wire is given to us. So this wire is on the curve y equals cx squared, and this is given to us, this c, and it's rigid, this wire. And on this wire is a bead, and this bead, there's no friction here, so this is frictionless. So this bead is sliding on this frictionless wire, and here we keep track of the, say, the x coordinate and the y coordinate of this bead. Maybe this bead has mass m, and there's gravity pushing down. And the question is, how does this move? Now, the way we address this question almost throughout this class is we try to get what are called the equations of motion. And equations of motion means you imagine you are given the state, you are given all positions and all velocities, and you try to find all the second derivatives of key quantities. So this turns into the question of what does x double dot equal in terms of x dot, c, g, m, whatever else we can think of. That means find the equations of motion. Then if we want to know how this moves, we have to solve the equations of motion. As a rule, the equations of motion will be nonlinear differential equations, and you will not be able to solve them. In some special cases, they will be linear, or there'll be some trick that you can solve them. But mostly, the goal is get the equations, then go to MATLAB and integrate them if you want to know how it moves. So our goal is to find the equations of motion. How do we do it? Draw a free body diagram. Substitute in the free body diagram formula for the quantities which show there, both knowns and unknowns, and then solve for the unknowns. The unknowns are going to be this x double dot. Okay, so how does this go? We draw a free body diagram. Free body diagram shows the bead like this, a dotted line like this. We've drawn it free. I didn't draw the free body diagram on top of this picture because then it gets confusing what forces are acting on what things. And I have here this force, and I'm going to call this force N E sub n, which means in the background I have to have a concept of what these directions are, E sub t, and here we have E sub n. And these are tangent to and orthogonal to the path at this point. Is there anything unclear about this free body diagram besides that I left off one of the forces? So somewhere down here I have to show that I've got some fixed frame where I'm going to do my calculations relative to, because it's the frame in which the laws of mechanics are valid, Newton's laws, so it's the fixed frame or the Newtonian frame. Yes, question?
Yes, does E sub t cross E sub n always E sub k, or
I guess it's like polar coordinates. If you set it up, if you're careful to make them so that they make a right-handed system, E sub t, E sub n, k, then you're fine. The convention is in 3 dimensions. See, in 3 dimensions, it could be k, could be minus k, whatever. So the convention is that E sub n points in the same direction as the acceleration, and E sub t points in the same direction as the velocity. And that's not necessarily right-handed the way you want it to be. Yes?
Isn't the velocity in the other direction?
Isn't the velocity in the other direction?
So are we assuming that we shot the bead out of the wire?
Okay, so unless you have a problem with dry friction, in which case, in order to draw the free body diagram, you have to know the slip velocity ahead of time. For most of the friction laws, force laws, and so on, we don't need to know the direction ahead of time. We just need a sign convention to make it clear. So is this bead going down the wire? Could go up, could go down. I might have just thrown it up.
But, so with the convention you just stated, ET should be in the direction of the velocity, right? So the bead should be moving.
Well, that convention with the assigned direction of velocity. So it's okay if I get a negative v in those formulas.
Okay.
Almost all the formulas we deal with work fine if you substitute in negative numbers. The exception is when you write f equals mu n, and you don't want to write complicated formulas with the sign of the velocity and so on, then you have to have the signs right. So f equals mu n is the one formula in this class that I can think of where you have to know the direction in advance of writing the equations. Does that address your question? Because who says which way the bead is going? So we'd like to write it in a way that works both ways, and let's just hope that all the formulas are not too dependent, or not dependent at all on the signs. I mean, where did you first learn this? Where I first learned this is in doing trig identities. You're trying to do things with sines and cosines, and you draw a picture in the first quadrant, and you figure out some identity. And if you have a very meticulous teacher, they will draw it in the second quadrant, the third quadrant, and the fourth quadrant. But you say, hey, it works out right. God is good. Math is good. The formulas that work in one place will work in another place. And you can check it meticulous if you want, but you don't. Just minus signs work for us as a rule. Who had one of those meticulous teachers who proved things in every quadrant? Okay. Okay. So how are we going to figure out how this thing moves? We're going to write the linear momentum balance equation. Linear momentum balance equation says that the sum of the forces is equal to the mass times the acceleration. What are the sum of forces? It's minus mg j plus n e n, and now we have the mass times the acceleration. So we can write this any way we want. The way I'm going to write it now is a rather straightforward, boring way. It's kind of the way you would do it before you took this class. So we're going to have to substitute in something here. We can write whatever we want for the acceleration. And I'm going to write d by dt squared of the position. That's what the acceleration is. And that's d by dt of d by dt of the position. And that's d by dt of d by dt of xi plus yj. That's the acceleration. But we know that we're stuck on the curve y equals cx squared. So if we know what x is, and we know what y is, and presumably if we know what x dot is and x, we know what y dot is. So for example, this turns into now d by dt of, now I'm going to take my first derivative here, that's x dot I, and then I'm going to take the derivative of this expression with respect to t, and that's 2x x dot j. See what I have done. Now we take the derivative of this. We get x double dot I plus, and now we have to use the product rule. So we get 2c x dot squared plus 2c x dot x double dot. And this whole quantity is multiplying by j. And that's the acceleration. Now if we take this whole expression now, which now says that minus mgj plus n e n is equal to m x double dot I plus 2c x dot squared plus 2c x dot x double dot j, and we look at it, how many equations do we have and how many unknowns? Okay, I'll make this the quiz. I'll call this equation star. Star has how many equations and unknowns in terms of things that we think we have given in this problem? Yes? The second term should be 2cx x double dot. You almost said that with enough confidence. Not quite. It was a little too much on the polite side. I think you were more confident of what you were saying than you indicated. Okay, so how many equations, how many unknowns? I'm going to put A, B, C, D, E here. And let's see. It could be, say, 2 and 2. It could be 2 and 3. It could be 3 and 2. It could be 2 and 1. And it could be other. Okay, and you guys vote. Let's do a no talking vote today. Ask me a question if you want to ask me a question.
What do you mean, how many unknown equations we have to use right now as you've written it, or explicitly?
Implicitly in the situation.
There may be things that are unknowns that we could maybe find out with another equation that we have written down.
I'm going to say right now as I've written it. And you can argue with me if you disagree with something. Okay, 10 more seconds. 5, 6, 7, 8, 9, 10. Okay. Most of you got this right, in my opinion, which doesn't mean that much. Which is that it's 2 and 2. At least in my worldview, it's 2 and 2. We have two equations. How do we say two equations? It's because it's a vector equation in 2D. And in terms of our way of thinking of this problem, even though ultimately we want to know x and x dot, when we're writing equations of motion, we think of x and x dot as given. They're not given, but for the equations of motion, they're given. We're going to hand them to the what happens if I can't talk anymore? We're going to hand them to the right-hand side function in ODE 2.3. So the unknowns here are x double dot and what's the other unknown? 1, 2, 3. Okay. Now we don't know n, and we're not trying to figure out the reaction force. At least right now we're not. So we want to get rid of it. So things that we don't know and we don't care about, we kill them. And how do we go about killing this term? Is we can take the dot product of both sides with something orthogonal to that n. So what's orthogonal to that n? Well, ET is orthogonal, and ET would work fine, but ET is defined as, say, the velocity divided by the magnitude of the velocity. And in this case, we know what the velocity is. It's x dot plus 2c x dot. And this is an I, and this is a j. And we can divide by the magnitude of that. So we divide by the square root of x dot squared plus 2c x dot quantity squared. And that we could use ET, but ET has all the square root stuff in it, and we're going to do the same thing to both sides of the equation. So it's just algebraically simpler to dot both sides with v. So we could use ET, but we would just have more stuff in there that would cancel out of both sides of the equation anyway. So we take this equation and dot both sides with v. What do we get? On the left-hand side, we get v dotted with minus mgj. And on the right-hand side, we get v dotted with this formula for the acceleration. And this is the thing we know. Now we do algebra, and from that algebra we get x double dot is equal to some function of x dot m g c, and that's all. And then we're done. And I'm going to skip that algebra. Does anybody have any questions about how to do that algebra? Let me just make it a little bit more clear. This is the v we're going to be using for that purpose. Any questions about this? Okay, so we get a messy nonlinear differential equation. So it's a problem that looks simple. It has a sort of hard answer, and the reasoning, it's not like the reasoning was impossibly difficult, but it's just not quite what they teach you in freshman physics. Yes?
When you plug in the position of the wire for the acceleration,
Yes.
assuming that all the acceleration is going along the direction of the wire, wouldn't there be a component of the acceleration that's kind of like circular acceleration, like kind of up toward the center?
Absolutely. That's what we find. So if you take this equation, that position is equal to, say, xi plus yj, and then we just skip a step and go to acceleration as x double dot I plus y double dot j, what you will find when you draw this vector is that it is not tangent to the path. It's not parallel to x dot y dot. So this is not parallel to x dot I plus y dot j. It would only be parallel if x dot and y dot were in the same proportions as x double dot and y double dot. But x and y are both functions of time as the particle moves around. So even though the formula has a parallel structure, the vectors are not geometrically parallel. I'm not allowed to go on with class until his muscles in the middle of his forehead relax a little bit. Okay, good. Happy with that? So yes, the acceleration is not tangent to the path, and that formula doesn't say it is. Any other questions about this question? How to do it? Questions means class ends, I get hit by a bus, a big storm comes, you lose your notes, all of a sudden you're in a crazy place, you can't find your friends or your textbook, and you have to do this problem. Could you do it? If you could not, then think, what piece is there that would make it hard for you? You miss your friends so much, you can't think about dynamics. Something else. Just one question. Just one question. Yes? Can you find the component of the force in the direction that it's moving? Yes, I can. And everybody in the class can too. That component is... I tried. You said it. That was one of those words that means what it says. They said nothing, which means that component is nothing. The force is normal to the wire. The velocity is along the wire. So the component of the force in the direction of the wire is 0. Of the reaction force, anyway. I assume that's what you're talking about. Is that your question? Could you find the component of the gravity force tangent to the wire? You could. And then what would you do with that? Okay, so an alternative way of doing this problem is you can write F is equal to ma. You can take the dot product of both sides with the tangent to the equations, but we've used that the acceleration has two parts. It's v dot et plus v squared divided by the radius en. This is true for any motion. That's true for any motion. There's always a part, if there's any curvature, radius of curvature, that there's an acceleration normal to the path. We can take the dot product of both sides with et, and we get that the dot product of the force is dotted with et. And in this case, the only thing which would come in is minus mgj, because the normal force, well, I'll just put it in here, plus nen, but that drops out. And then we get m v dot et, and then this drops out. And v dot is the rate of change of speed, and another way to write v dot is this equal to the arc length double dot. So the rate of change of arc length, the rate of change of speed, is in fact the dot product of the gravity force with the unit tangent vector. Does that address your question? Now, if you wanted to find out how that changes in time, then you have to figure out how the tangent vector changes with arc length, and the expression for arc length is very complicated. It's not that complicated, but you have to go back and figure out x in terms of arc length, or arc length in terms of x, and so on. Does that address your question? Okay, thank you. I don't know if that qualifies as a hit by the bus kind of question, but at least it filled the time. Okay, so let's do another example. And this is an example I did before. I did it before with polar coordinates. Now we're going to do it using moving reference frames. So this is a new gun, what I call new gun, because that stick with the nut sliding on it, remember that? It goes very fast, and you don't see those in the stores yet, so it's this new product we're going to use for a new way of killing people. And the picture is going to go like this. We're going to imagine that we have a motor here. I'll draw it like a motor instead of just like a hinge. And the motor is connected to a stick. And this stick is going to rotate, and this bead is going to fly off the stick. And again, we're interested in figuring out how this thing flies off the stick. But instead of using polar coordinates, let's take this as a problem with moving coordinates. So what I'm going to do is I'm going to say I have my fixed coordinate system, x and y, and associated with that, I've got my unit vectors, I and j. And now I'm going to take a moving coordinate system, and for my moving coordinate system, to keep it simple, I'm going to put it also on the same point, O prime, and I'm going to draw unit vectors associated with that system, and I'm going to call those I prime and j prime. And then I have associated with those motion x prime and y prime. So this is what I'll call my fixed coordinate system, this xy coordinate system, and this is what I'll call my body coordinate system that's connected to the object. Now I'm trying to turn the word body into object in mechanics. It's a crusade, me against the world, but I don't want to do it here. I don't want to call the reference frame O, because we use O for too many things, so I'm stuck with the word B. B for object. Object, B, body. Okay, so now we'd like to figure out how this moves. Let's say this is frictionless. Let's say there's no gravity. And we're trying to find the motion. How are we going to find the motion? That we're going to find what we call the equations of motion, which means we just want to solve for the accelerations given all the positions and so on. Now let's say somebody tells us ahead of time that this angle theta is equal to some omega 0 t, where omega 0 is a constant. So we're going to spin this stick at a constant angular velocity to make it a little simpler a problem. So we're trying to find these equations of motion. And how are we going to do it? Well, we're going to start out with a free body diagram. So a free body diagram of this thing looks like this. I cut it free, and I show this force here, and that force is in the nj prime direction. And if I wanted, I could put other little things here, but I think it's clear enough what the direction is indicated. Okay, any questions so far? Okay, then we want to use F equals ma to figure out what the motion is. So we'll use linear momentum balance. Linear momentum balance says that the sum of forces is equal to the mass times the acceleration. What are the sum of the forces? They are just n e sub n. And what's the mass times the acceleration? It's the mass times, now we're going to use the 5-term acceleration formula to calculate the acceleration. What did I do wrong? I think just notationally, I was trying to get away from these polar coordinates to get you into these rotating coordinates. This is j prime. Now we want to plug in the 5-term acceleration formula. The 5-term acceleration formula has a bunch of terms in it, 5 of them. One of them is the acceleration of O prime with respect to O. Then we're going to add to that the acceleration of the particle p with respect to the moving frame. Then we add to that 3 terms which have to do with the rotation of the frame. One of them is the centripetal term, minus omega squared of the position of the particle with respect to O prime. One is for the angular acceleration, omega dot, cross the position of p with respect to O prime. And one is the Coriolis force, 2 omega cross the velocity of p relative to the moving frame. Now we'd like to fill in all of these 5 terms. Okay, so in order to plug in this formula, we have to understand each of these terms. Okay, I would like you to all think about what the first term in this equation is. I'm going to write down these 5 terms like this. What is this first term? Okay. You understand me. What's the second term? You can ask a question about the first one if you're not clear about the first one. At any time, you can ask a question about previous terms. Okay, who thinks they know what the second one is? Raise your hand. Who does not know the second term yet? Raise your hand. Who is thinking about the second term in a productive way at this moment? Raise your hand. Okay, so. Yes? Here? Okay, so the question is, what's the difference between, let me stick with velocity, what's the difference between p with respect to, say, O prime and p with respect to some moving frame? What's the difference between these two terms? The definition of this one is the velocity of p with respect to the fixed frame minus the velocity of O prime with respect to the fixed frame. And the definition of this one is x prime dot I prime plus y prime dot j prime. Body frame is the moving frame. So one of them is the difference between velocities in the fixed frame, and the other is this concept of velocity relative to a moving frame, which is not the ordinary subtraction definition of the word relative. It means, what does the velocity look like if you are on the moving frame and oblivious of anything on the outside? And you calculate that by looking at the rate of change of the coordinates in a coordinate system which is glued to the moving frame. Yes?
As we're defining O prime, isn't O prime glued to the moving frame?
It is.
So, as far as we're concerned, is there any difference between P with respect to O prime and P with velocity?
Yes. In this problem, there are two different things. The velocity of p with respect to O prime, it would be, this thing in the end is going to be moving in some curved path. The velocity of p with respect to O prime is in that direction. The velocity of p with respect to the moving frame is in that direction. Because we look at we get on board here, we look at the coordinates here, and we look at the rate of change of those coordinates. So this term here is x prime double dot in the I prime direction, which is different from the velocity of p with respect to O prime. We could have a more precise notation which would help, but then it gets very confusing. We should never actually write velocity without saying what reference frame we're using. So whenever there's no script F or script B, there's a script F which is implied. Okay, any questions about this second term? Yes?
Do we need the prime on x and I, or does the prime on I automatically denote that?
No, we need the prime on both of them because this is a thing and this is a thing, and we're multiplying the two of them together. So this is a unit vector which is changing in time, and this is a distance which is changing in time, and it's the product which is this vector.
Is x prime and x prime? As long as we denote we're moving in the I.
Yes, x prime is this distance here, and x is this distance here. They're two different numbers. Yes? If I put r double dot, I would have to say I'm using r in the coordinate system, which is beta. Not beta, I fell for that, which is the script b coordinate system. This is not a dot product. This is a product of a scalar and a vector. Could I, if I wanted to write r of p with respect to O and then take the derivative of that, I can talk about the derivative, but then I have to separate out the meaning of the derivative in terms of whether I'm going to represent it in the fixed frame or the body frame. So the key thing is if I put dot here, implicit in that is I'm taking that derivative in the fixed frame, and the meaning of that is omega cross that position p with respect to O plus the derivative as calculated in the body frame. And what does that mean? It means take the derivative of the components, not of the base vectors. So if I wanted to use this as a concept, I'd have to use it together with this as a concept. Okay, what's the third term here? Think about the third term, please. Okay, what is the position of p with respect to O prime? It's just this omega is omega 0, so that's squared, and that position is just x prime I prime. What's the fourth term? Well, I gave you that omega was a constant, so omega dot is 0. And what's the fifth term I have to put here is 2 omega 0 k crossed with this relative velocity. So I've got to cross it with something here. I'd like you to fill in what I have to cross it with. Okay, who has got that term filled in already? Who has not? Okay, most of you have it. This is x prime dot I prime. Who had this correct? Okay, good. Then you're getting the hang of it. Then we have this here like so. Now we'd like to get from this equations of motion, well, don't know it, don't care about it, kill it. How do we kill it? We dot with J prime. So we take this, dot with I prime. So I take this whole formula here, and I take the dot product of both sides with I prime. What does that give me? On the left-hand side, it gives me 0. I dot this with I prime, I get 0. I dot this with I prime, I get x double dot prime. I dot this with I prime, I get minus omega 0 squared x prime. I dot this with I prime, I get 0. And I dot this with I prime, and I get, because k crossed with I prime is j prime. Look at that, x, that's confusing. K crossed with I prime is j prime, dot with I prime gives 0. So here's my differential equation. Look at that differential equation. It's the standard, I can write it like this, x prime dot dot is equal to omega 0 squared x. So this implies, say again, what happened to mass? Drops out. Because we had 0 on both sides. If you like, I can go like this. So this tells us that x prime is equal to, say, x0 hyperbolic cosine of omega 0 t plus v0 hyperbolic sine of omega 0 t. And I think I have to divide by, when I differentiate this, I get an omega 0 on the top, so I have to divide by omega 0. Okay. Any questions about this? So you can compare this to what we did with polar coordinates, and you'll see all the terms match somehow. It's just a different way of doing the problem. Now, at the beginning of doing this problem, just 15 seconds more, I picked my moving coordinate system to be like this. I could have done this problem just as well if I picked the moving coordinate system to be identical to the first coordinate system. All the details would be different, but all the calculations would be the same. And I could have picked the moving coordinate system to be out here a distance 17.6 feet, rotating with this, and I could have picked it crooked any which way. You should try a few different coordinate systems and see that you get the same answer in the end, no matter what coordinate system you use for the moving coordinate system.